acidic strength of phenols. See, in amines we saw the ortho effect, that is base weakening effect, but in case of phenol there is no such effect. So there is no ortho effect in phenols, but in phenols, you know, it is acidic because, why is it acidic? Yes, because phenoxide ion is more resonance stabilized than phenol. So phenoxide ion, because it is more stable, because there is delocalization of negative charge only, and so on, there are, but in case of phenol, when resonance takes place, there is separation of charges. It is like this, and so on. There are resonating structures where there is separation of opposite charges. But in case of phenoxide ion, there is delocalization of negative charge. That's why phenoxide ion is more resonance stabilized than phenol, and that is responsible for acidic nature of phenol. Now, if phenoxide ion is stabilized by some group, that will increase the acidic strength of phenol, because more stable phenoxide ion, that leads to the forward reaction, and therefore removal of H plus ion is easier. So obviously phenoxide ion, as it is negatively charged, so electron withdrawing groups increases the stability of phenoxide ion, and that's why electron withdrawing groups will increase its acidic strength. Means phenol is more acidic if electron withdrawing groups are attached, like minus I effect or minus M effect. Groups having minus I and minus M effect, if net effect is electron withdrawing, then phenol becomes more acidic. And if there are electron releasing groups, you know, electron releasing groups decreases the stability of phenoxide ion, because it will, yes, plus M or plus R, minus M, sorry, plus M, sorry, plus M or plus R, or hyper conjugation. So all the three are electron releasing effects, and therefore decreases the stability of the phenoxide ion, and that's why phenol becomes less acidic if electron releasing groups are attached to it. So in short, simple method is that electron withdrawing groups increases the acidic strength, and electron releasing groups decreases the acidic strength. Electron withdrawing groups increases the acidic strength, because these groups increases the stability of phenoxide ion. Yes, OH is already a smaller group. No, it is related to steric hindrance. Yes. Okay. Now, if in first case we take into account the groups having minus M as well as minus I effect. Minus M and minus I effect, or we can say minus R minus I effect. So in these cases, there are NO2 group, CHO group, C double bond, COR or CN, because in all the cases, if we look at NO2, in NO2 we have nitrogen oxygen pi bond. In CHO there is C double bond O. In COR again C double bond O. And in CN, so in all the cases there is a pi bond, so that will account for minus R effect. So whenever the atom directly attached to the ring has pi bond with other atom, that group has minus R effect. Same because nitrogen sp2 hybridized carbon attached to more electronegative oxygen. sp2 hybridized carbon attached to more electronegative oxygen. sp hybridized carbon. So they are more electronegative than sp2 hybridized carbon, and that's why they have minus I effect. In inductive effect, we take into account electronegativity only, and in minus R effect, we take into account pi bond attached to the atom directly attached to the ring. And if atom directly attached to the ring has a lone pair, then that group has plus R effect, like NH2, okay. Now there is NO2 group at ortho position of phenol, meta position of phenol, and para position of phenol. So obviously A, B and C, all the three, they should be more acidic than phenol itself. In case of ortho, there is minus I as well as minus M effect. In meta position, there is only minus I effect, and in para, there is minus I as well as minus M. So in case of ortho, there is a intramolecular hydrogen bonding. There is intramolecular H bonding. So due to intramolecular hydrogen bonding, removal of hydrogen becomes somewhat difficult. Now, there is a strong electron withdrawing effect at ortho and para position. So obviously ortho and para, they are more acidic than meta, which in turn more acidic than phenol itself. Means ortho and para nitrophenols are more acidic than meta, because in meta there is only minus I effect, electron withdrawing effect due to minus I effect only. But in case of ortho and para, there is minus I as well as minus M. Now out of ortho and para, which one is more acidic? Para would be more acidic because there is no intramolecular hydrogen bonding. Minus M means minus R. Minus M and minus R are same. So in case of ortho, there is minus M and strong minus I, but at the same time there is hydrogen bonding. But in case of para, there is minus M as well as weak minus I. That's why order is para, ortho, meta, phenol. So ortho is behind para because of intramolecular hydrogen bonding. Okay, next is again they are electron withdrawing groups, but there is no mesomeric, or we can say resonance effect. So in this case we compare only minus I. So obviously minus I effect of the group closer to it is more. So ortho group, the group present at ortho has more minus I effect than meta than para, because there is only inductive effect. So ortho is more acidic than meta, meta is more acidic than para, which in turn more acidic than phenol itself. So ortho, meta, para and then phenol. Now again electron withdrawing effect, there is minus I effect and plus M, because you know fluorine, chlorine, bromine, iodine all have lone pairs. So whenever atom directly attached to the ring has a lone pair, that has plus M, or we can say plus R effect. But because fluorine, chlorine, bromine, iodine all are more acidic than carbon, so they have minus I effect, and in case of halogens, inductive effect is dominating over mesomeric or resonance effect, and that's why all the ortho, meta, para are more acidic than phenol, and obviously ortho should be more acidic than meta than para because it is closer to the OH group. So order is always ortho, meta, para and then phenol. Yes. OH, now CH3 at ortho. One thing keep in mind, when we have fluoro group, in that case, you know, fluorine at ortho would form hydrogen bonding. Then ortho fluorophenol is almost closer to phenol itself, because there is more minus I, but at the same time plus R is also very large, because here there is 2p and 2p overlapping. So resonance is very close to, means dominance of minus I and plus R is almost equal. That's why it is as acidic as phenol, or almost, in case of ortho only, fluoro only. In rest cases it is ortho, meta, para and then phenol. Now alkyl group. Alkyl group has plus I effect and hyperconjugation. So obviously at ortho position there is hyperconjugation as well as plus I effect. In case of para again there is hyperconjugation and plus I effect, and both the effects destabilize the anion. So tell me, what is the order of acidic strength? Yes, phenol should be more acidic, then it is meta, and then para, and at the end it is ortho. Now plus M and minus I. As I said, OH, you know, OH, O has lone pairs, NH2 again lone pair, OR again there is lone pair. So in all the cases atom attached to the ring has a lone pair, and therefore they have plus M, or we can say plus R effect, and oxygen, nitrogen both are more electronegative than carbon, that's why they have minus I effect, but plus M is dominating over plus M is dominating over minus I. So see, plus M minus I plus M weak minus I. So what is the order of acidic strength? Obviously at ortho it is electron releasing. Here electron releasing, but in this case it is electron withdrawing. So obviously meta should be more acidic than phenol, and then it is ortho, and at the end it is para. This hydrogen bonding is not as effective as in case of if it is attached to NO2, because you know OCH3 there is hindrance, due to steric hindrance hydrogen bonding is least, that's why it is not very effective. Okay, first is NO2 having minus M effect dominating over minus I, but both are in the same direction. In case of CCl3 it has minus I effect. In case of chloro it has minus I, which is dominating over plus M. CH3 has hyperconjugation. OCH3 has plus M effect, which is more than minus I. Obviously most electron withdrawing, strong electron withdrawing group is NO2. Then it is CCl3. Now out of CCl3 and chlorine, you know CCl3 has strong minus I effect due to the presence of 3 chlorine groups. It has chlorine directly attached to the ring, but at the same time it has plus M effect, which compensate for minus I, and that's why CCl3 is more electron withdrawing, has more minus I effect than Cl itself. Now CH3 and OCH3 both are electron releasing group. This is electron releasing due to hyperconjugation and plus I, and it is electron releasing due to plus R, or we can say plus M. So obviously this OCH3 is more electron releasing than CH3 itself, and that's why this one is more acidic than methoxy, paramethoxy phenol. What is the order of acidic strength? One first is NO2, then CCl3, Cl. They are at meta positions. Which one? Fifth one is, yes, fifth one is least acidic because even at meta position it has plus I effect. All have minus I. Okay. Write the whole order. See, it is first one is most acidic, then it is second, then it is third, fourth, third and sixth, because all are minus I effect, and minus I effect of NO2 is more than CCl3, CCl3 is more than Cl, Cl is more than OCH3, because in OCH3 oxygen is attached to CH3 group which releases electron towards oxygen, and then it is fourth and least is fifth. Okay. NO2 group at ortho position, CCl3 group at ortho position, Cl group at ortho position, CH3 group at ortho position, OCH3 group at ortho position. In first case there is minus I as well as minus M. In second case there is only minus I. In third case there is minus I, and that is dominating over plus M, and there is dipole-dipole interaction. OH and Cl, there is no hydrogen bonding, but there is dipole-dipole interaction. Then it is CH3, and last it is plus M. And I told you hydrogen bonding is not as effective as in case of fluorine or OH or NH2 or NO2. Yes. Acidic, most acidic is ortho. Okay, great. Because right. It should be first, second, third, fourth, fifth, and sixth. Yes, because NO2 has minus I as well as minus M, and CCl3, out of CCl3, Cl and OCH3, you know, CCl3 group has only minus I effect, but in chloro and OCH3 they have minus I as well as plus M. But here in chloro minus I effect is dominating over plus M, but in OCH3 plus M is dominating over minus I. So it is first, second, third, and then it is fourth and fifth and sixth case. CH3 and OCH3 both are electron releasing groups. Yes, OCH3, CH2OH and OCH3. So obviously phenol is more acidic than this one is actually alcohol, and phenyl group has minus I effect here. In this case there is no acidic hydrogen, so ether is least acidic. Phenol, alcohol and ether. In fifth case, you know, there are two methyl groups at ortho and NO2 group at para. But in this case, two methyl groups at meta and NO2 at a, but you know, because of the presence of these two bulkier groups at ortho position of NO2, its resonance is least. It is not involved in resonance because of the presence of two methyl groups at its ortho with respect to NO2. So that is called SIR, steric inhibition of a resonance. So resonance is sterically hindered and it is steric, there is steric inhibition of a resonance. So obviously if NO2 has minus M effect in case of a first, where there is no SIR effect, and that's why it is more acidic than in case when NO2 attached to the benzene ring and there are methyl groups at its ortho position, because NO2 go out of plane due to the presence of these groups. Okay, OH, NO2 groups at ortho and para positions. There is one position positioned at ortho, other is positioned at para, and then it is meta. In third case, NO2 groups. Here there is minus I minus M, minus I minus M, minus I minus M. But in this case again minus I minus M, minus I minus M. In this case it is only minus I. Here it is only minus I minus I minus I minus M, but again there is somewhat SIR effect because this NO2 goes out of plane due to the presence of these bulkier groups. There is somewhat SIR effect, and that's why first is more acidic than yes. Reaction. So this is all about acidic strength of phenols. So reaction of phenols with salts. So say if we have a salt like salt of NaX and it is a salt of strong base and weak acid, and when it reacts with strong acid then reaction take place. Means if we have a salt of strong base, weak acid with strong acid, then weak acid is replaced by this, we get the salt of strong acid, salt of strong base and strong acid, and weak acid we get back. For example, NaCl when react with H2SO4, we get Na2SO4 and HCl, because H2SO4 is stronger acid than, but if Na2SO4 is treated with HCl, then there is no reaction. So stronger acid displaces the weaker acid from it, any metal salt, and weaker acid is released out as a gas or liquid or precipitate, whatever it is, even as a solid. So weaker acid cannot displace stronger acid from the salt. See, in first case, sodium acetate, it is a salt of strong base and weak acid. So when it is treated with methyl sulfonic acid, this reaction is taking place. We get weak acid, that is acetic acid, along with salt. But if we have sodium acetate and we treat it with phenol, you know, if we compare acetic acid and phenol, which one is more acidic? Acetic is more acidic. Therefore, this reaction cannot take place, because phenol is weak acid and acetic acid is comparatively strong. Both are weak acids, but if we compare both of them, then acetic acid is stronger than phenol. Why is it so? Why acetic acid is stronger acid than phenol? Yes, phenoxide acetate ion has more resonance stabilization than phenoxide ion. Acetate ion is more resonance stabilized than phenoxide ion, because acetate ion, that it gives equivalent structures, but in phenoxide, negative charge in resonance, negative charge moves from more electronegative oxygen to less electronegative carbon, and that's why phenoxide is less resonance stabilized. Next is phenol along with paranitrophenol, sodium salt of paranitrophenol. So obviously, you know, paranitrophenol is more acidic than phenol. That's why reaction cannot take place, because weak acid cannot displace strong acid from the salt. Again, sodium salt of benzene sulfonic acid and benzoic acid. So obviously, you know, sulfonic acid is stronger acid than benzoic acid. So benzoic acid cannot displace sulfonic acid from its salt. Next is sodium salt of acetylide and water. So that means acetic acid, this acetylene along with sodium hydroxide, this reaction is possible. But almost acetylene and water have almost same acidic strength, so that's why it is written as a star, that reaction can take place to some extent. because water is stronger acid than acetylene. Okay, so that's all about today's session. In the next class, we will do the acidic strengths of carboxylic acids and benzoic acids. In benzoic acid, even there is a ortho effect, that is acid strengthening effect. Okay then. Yes, I will send. Today it's not possible. Tomorrow in the morning, are you free? Yes. Okay, so around 9 o'clock.